Alright guys, so we're going to be going over maximum shear stress theory, or MSS, and the source and energy theory, you call it the YouTube. For ME304 machine design, we use the Shigley book, and so if you happen to use that, or have ME304 at Embry-Riddle, go ahead and pull that book out. So the crank shown is loaded with a force of 300 pounds, which is induced both bending and torsion in the 0.75 inch. So on and so forth, steel, fixed at point A, find the margin of safety for the stress state based on maximum shear stress theory and distortion energy theory, and then compare those results. Okay, so you guys can see that this is 4 inches, this is 1 inch, this is 5 inches, 5 inches, this is a 3/4 inch rod, this one's well, we don't need that for anything. 3/4 inch, and the pound, the force is 1 inch from there. Okay, so yes, 1 inch. That should be all the measurements you need. I'm going to pull this off to the side here so that I can do the math. So, drawing a Freebody diagram, what we do is, what I'm going to do is I'm going to reduce this down to this basic, more basic stuff. I'm moving the force over down that this rod over here, moving the force back down here and extending it out to where it would actually be if I was to translate that force. It makes it a little bit easier. I know there's going to be a torque here induced by the force, and then back here at A, I'm going to call this A, B, and I don't know what I'm going to call that yet. That's just out there. We have a reaction at A. Oh, sorry, reaction at A. Point A. Get that done. And then we have an opposing torque. We're going to call that one TA. And this one's TB. Great nomenclature. Alright, so the torques are equal to the force times 4 inches, which is equal, this is actually, the torque is equal to force times 4 inches, because the force is normally out here 4 inches away. If you want to go back to the video and draw out that picture, or screenshot that picture so you have something to look at, go ahead. I'm just going to go right through this, which is equal to 300 lb times 4 inches, which is equal to 1,200 inch-pounds. 1,200. Alrighty, we're assuming that counterclockwise is positive, so then the sum of the torques is equal to TA minus TB is equal to 0. So using this up here, we find that TA is equal to this one was actually equal to TB. TA is equal to 1,200 inch lb. Okay, inch pounds. Now you'll see that there's kind of a sign discrepancy here. One should be opposite to the other one, but this is actually, well, I don't really, you can go ahead and assume in whichever direction. I just changed the rotation of these so they are both positive, because I assumed them in the correct direction. If I assumed them both in the same direction, then I'd find out that one was negative in order to oppose the other. So that's why these are both positive. Okay, so then some of the moments about A, let me even this up so it's like straight on your screen, is equal to MA minus F of 6 inches equal to 0. So MA is equal to 300 pounds times 6 inches equal to 1,800 inch-pounds. Coolness. Going to need that. Going to need that. I'm going to underline that too. That's 1,200 up there, by the way, in case you can't see that. Alrighty. So I'm also going to calculate I for this beam. I'm getting the basic constants out of the way because we're going to need all of these. So I over 64, which is equal to pi times 3/4 of an inch, 0.75 to the 4th over 64. And that was the diameter of this rod right here. So I is equal to 0.0155 inches to the 4th. J, because we'll need J2 here for tau, is equal to 2I, which is equal to 0.031. Okay, so I need to find the stress, the torsional stress, and the axial stress. So sigma x for the standard stress is m r over I. And I know what m is, and it's the only m, so I don't have to do like m max or anything. This is the only m in the entire beam, so I know it's m max. And I took it at point A, and I know that's going to be the maximum moment acting around point A. So then moving on, and then tau xy is equal to t times the radius over j. So putting in those values is 1800 times 0.375, which is the radius, 0.0155 inches to the fourth. And then this one is 1800, oh no, sorry, equal to 1200 inch pounds, 0.375 inches. Can't see that at all, can you? All over 0.031 inches to the fourth. You want to do it like that. So then we're going to find out that tau xy is equal to 516.13 lb per inch squared. And then sigma x is going to equal 43548.31 lb per inch squared. There we are. So we have those two values. So now we have everything we need to do maximum shear stress, and well, no, not everything. Now we have to find the principal stresses. So using those values, principal stresses, which we're going to call sigma A and B, are equal to sigma x all over 2 plus minus square root of sigma x over 2 squared plus tau xy squared. So that's the basic principal stress equation. Normally this would be sigma x plus sigma y and sigma x minus sigma y. But since there is no stress in the y direction, we can cancel it out and ignore it. So it just reduces down to this, which makes it a lot easier for us. So then this is equal to 4354.8.31 over 2 plus minus the square root 4354.8.31 over 2 squared plus 1451.6.13 squared. Just like that. And if you calculate that all out, you'll find out that sigma A is equal to 47943.53 lb per inch squared, and sigma B is equal to negative 4395.13 pounds per inch squared. Okay. So now, moving on, in the text we need to find out what the ultimate yield strength is, because we're going to need it here in a second. So if you're using the Shigley book, it's actually 62 KSI from Appendix 20 in the textbook. So if you want to go look that up and figure out how to use those tables, you need that. Your instructor is probably going to force you to learn to use those tables, so I recommend it. Okay, so now we have all the basic values that we need. So for part A, for maximum, excuse me, can't talk. For MSS, hang on, I gotta check all my notes, make sure I got the right stuff. So yes, maximum shear stress theory. The calculation that we're going to be doing. Okay. So there's several conditions for maximum shear stress theory that you have to look at based on sigma A and sigma B. In our case, we see that sigma A is greater than 0 and sigma B is less than 0. So that is case 2 by MSS. So within case 2, you end up with an equation. You have sigma 1 minus sigma 2 must be greater than sigma 1 sy over n. But we're looking for the margin of safety, MS. MSS and MS, that's handy. So what this is, we're going to change this equation a little bit to MS is equal to SY all over sigma 1 minus sigma 2 times N minus 1. And this is the factor of safety, so the allowable or the predicted times the factor of safety minus 1. Now, if we do this calculation of sigma 1 minus sigma 2, this one over here, so 47 minus the negative this, you'll end up with 52 by 232 psi. So this is what this value is, so make that clear. So subbing this in down here and using the SY that we found up here, you can find out the margin of safety is equal to 62. I'm just going to turn this into 1,000 because that's what we're working with. And then 52 over 232 times N, and the factor of safety we were given at the beginning of the problem is 1.2 minus 1. And if you calculate that out, you'll find out that the margin of safety is equal to 0.010. Negative 0.010. I apologize. Which means that it's going to fail because the margin of safety is too low by the maximum shear stress theory. So it's going to fail. So now, moving on to distortion energy theory, part B. If we do it with distortion energy theory, you first have to find the von Mises stress, so DE theory. And in order to find von Mises stress, you're able to use the original stresses that we calculated clear back at the beginning of the problem back here, so sigma x and tau xy. So for von Mises stress, it's denoted as a sigma prime is equal to sigma x squared plus sigma y plus sigma y squared plus 3 tau xy squared, all to the 1/2. Now, there were no sigma y forces, so both of these go to 0, which simplifies our equation quite a bit. So sigma x squared plus 3 tau xy squared, all to the 1/2, is going to be our von Mises stress. So if we calculate that out, we know that sigma x is 43.460 squared plus 3 times 14.4 by 14,486 squared. Take the square root of that, and you'll end up with von Mises stress equaling 50 by 183 psi. So pretty easy. And once again, for DE theory, you use the same kind of a margin of safety formula that we used before, which is equal to SY all over von Mises stress times N minus 1. So if you calculate that out, you end up with 62. I'm just going to go KSI this time. All over 50 point, rounding up KSI to KSI times the same margin of safety minus 1. And you end up with a margin of safety of 0.029, which is positive, so it shouldn't fail, but it's very close. So it's okay, but just barely. You usually want margin of safety of about 0.5 or better if you're doing real engineering. So just barely okay. So if you're looking at this, which one is more conservative, or how they compare, you can see that MSS theory is a lot stricter in that you have to have more material or better standard quality materials in order to be successful, otherwise it's going to cause you to fail, as opposed to DE theory, which lets you kind of get away with it with the very minimum, even though MSS theory doesn't allow you to do it. So as far as the comparison goes they're actually decently close. I mean, if you look at the difference between them, you've got 0.029 and negative 0.01. So there's a difference of 0.03 between the two of them, but that changes as you get bigger and bigger in those margins of safety. But there you go. That's how you use maximum shear stress theory and distortion energy theory.